I want to take a look at a new mathematical concept, and that is something called a function. Now, to understand a function, we need to first start out talking about what a relation is. And with a relation, basically all that is any set of ordered pairs. In other words, with a relation, you have an input, you have an output, and they are put together not following any particular rule. Now, our inputs and outputs, as we commonly call them, are going to be more formally called domain and range. So, for example, with a relation, all of the values that you put in is going to make up a set called the domain, and everything that comes out is a set called the range. Now, with a relation, or even sometimes with a function, you don't always have to use numerical values. An example of a relation would be a domain that consists of 4 names: Carol, Mary, John, and Alan. And the range could be the seats that they're going to be assigned to in the classroom. With a relationship, there's no restriction about how you make these assignments. You could take Carol, assign Carol to seat number 1. You could assign Mary to seat number 3. Assign John to seat number 2, and assign Alan to seat number 4. And you would have a relation, again, where the domain is this set of names, and the range is going to be these 4 seats. Now, to have a function, we need to put a restriction or put a tighter definition on than what we had with relation. A function is a set of ordered pairs in which each first component corresponds to exactly one second component. Or, in other words, each input has exactly one output. Or each element of the domain is associated with a unique element of the range. However you want to state it, with a function, every input has exactly one output. Now let's look at an example that would give us instead of a relation, like we had before, let's look at an example that would instead give us a function. We're going to come up with a domain here, and I think I'll let my domain be a set of cars. We could have a Honda, we could have a Ford, we could have a Chevy, a Dodge, and let's be exotic, let's have a Porsche. Now my range is going to be a set of price tags. Let's say we've got a $30,000 price tag, gonna $25,000 price tag. We're going to have a $42,000 price tag, $75,000 price tag, and a $12,000 price tag. Now with a relation, I could take these inputs and put them with the outputs in any way that I choose. But with a function, every input has to have a unique output. In other words, the Honda could go to the 30,000. The Ford could go to the 42,000. The Chevy could go to the 12,000. Now this is nothing different from what we've seen with a relation so far. But with a function, what you would not see, once we map the Chevy to the 12,000, we would not turn right around and map it to the 25,000 as well. Again, as our definition said, each input has exactly one output. So once the input Chevy has been mapped to 12,000, it can't be reused. In other words, elements of the domain, inputs, cannot be reused. So we have to go back and say, well, now since the Chevy has already been given a price, I cannot go back and do something different. I must stick with the price. So we would use the $25,000 for the Dodge and the $75,000 for the Porsche. Now let's say there was another car. All right, you get a new car in, and this time we're going to have a Toyota. We don't have any more prices. Well, we could add one, or we could use one again. In other words, I could take the Toyota and map it to the $30,000 just like I did the Honda. And that would not violate the definition of function. With a function, elements of the domain cannot be reused, but elements of the range can be reused. I can use this 30,000 as many times as I want, as long as none of these brand names get reused. Now let's look at an example of a function using ordered pairs for the example. The map is easy enough to look at and hopefully understand what's going on there, but let's look at some ordered pairs. Let's say I had a set of ordered pairs, the set being 1, 2 for the first ordered pair, 2, 4 for the next ordered pair, 3, 6 for the next, 4, 8 for the next. So far what I have is a relation, and it is a function as well. Let's keep going. And again, I'm not saying that this ordered pair is a function, or that one, or that one. When you talk about something being a function or not, you're talking about the entire set collectively. Alright, so my next ordered pair, I'll make that a 5, 8. The next ordered pair, I'll make it a 6, 8. And again, let me ask the same question. If you look at this set of ordered pairs, do I have a function? And so far, you do. Yes, the 8 has been reused there, there, and there. But the 8 is in the range. It is an output. That can be reused without any problem whatsoever. I could add one more ordered pair and make this from being a function to no longer being a function if I just violate the definition. And again, that definition being each input has exactly one output. So what could we do? Well, we could go back and take a input we've already used, for example, the 3. It had a 6 with it the first time. If I come in here and put something different with it, then the fact that the 3 has been reused with 2 different outputs makes that no longer a function. So that's the type of thing you have to watch out for. Now we could just sort of imagine creating a set of inputs and outputs and see if we can sort of hypothetically think about whether the set that would be created would be a function or not. Let's say I was to create all the ordered pairs that I could, where the first element of the ordered pair was a baseball team or a football team. The second element of the ordered pair would be a player on that team. Now, if I created all the ordered pairs that I could in this fashion, would that be a function? Well, it wouldn't, because for any team you pick, any input that you pick, any element from the domain that you pick, there's going to be a number of players that you can put with it. So this would not be a function. Now, if you were to turn it around, though, and say I'm going to create all the ordered pairs I can by picking a player first and then naming the team that that player is on right now, then this is a function, because it is impossible to pick a player and name more than one team that they're currently on. Sure, they can be on different teams over time, but as of right now, each player is only on one and only one team. So that would form a function. Now, another way we can work with functions is graphically. It's actually fairly easy graphically to tell whether you're dealing with a function or not. It's pretty easy to see. I'm going to look at two graphs. I'm going to show you two graphs. One of them is the graph of a function. one of them is not. Let's see if we can figure out which one is which. And I'll even give you the equation that describes the graph. So let's take a look at that next. Get this last example cleared off. Here we go. First, x equal y square. The graph of x equal y square would be a parabola. Let's draw the graph in a different color so we see where it is. So there it is. The graph of y equal x squared, as a matter of fact, is also a parabola, but it's oriented slightly differently. Again, drawing in the other color, it looks more upright. Now, one of these is a function, one of them is not. Wonder which one is which. Well, if you stop and look at the graphs, if you pick a x value, any x value you want, for this particular graph you notice that there's a point right here that uses that x value, and it has a y with it. There's an x and a y right there at that point. And down here you notice, since it's directly below, that this is another point that uses the same x, but there are two different y's. So this graph is not a function. Now over here, if you pick any x value, you'll notice there's one and only one point on the graph for that particular x value. Now sure, for y values, there's more than one point corresponding to y values, but again, y is in the range. It's the output. That doesn't matter. So this one is a function. And there's a simple test that can be used called the vertical line test. The vertical line test says that for any graph, if you can pass a vertical line through it somewhere and hit it more than once, it's not a function. So for example, with this graph, right here, I hit it twice, not a function. Right there, I hit it twice, not a function. Over here, you can put a vertical line anywhere you want. You'll never touch it more than once. That's why it is. So let's look at some other graphs. Let's say I had the sine wave being graphed. Sine wave is one that you will see if you were to ever, say, take a trig class in the future. Sine wave, and I'm not doing the best job of drawing it by hand, looks something like that. Is the sine wave an actual function? Well, let's see. Can't hit it more than once there. Can't hit it more than once there. Not there. Not there. Not there. I can't see anywhere I could hit this thing more than once. So your sine wave is a function. Let's look at another graph. If you take a class where you study conic sections, one of the conic sections you will study is that of an ellipse. It's basically a circle that's been elongated. Is an ellipse going to be the graph of a function? Well, let's see. I can hit it twice there. I'm done. It's not a function. Any graph that you can hit more than once with a vertical line isn't a function. Don't confuse this vertical line test with, say, a horizontal line test. There is a such thing as a horizontal line test, but it tests for something totally different, something we are not going to look at anytime soon. So make sure you keep your lines vertical when you're testing for functions. Now, one other thing with functions we need to look at, that is function notation. Alright, well now with function notation, you take an equation that you've been writing as, say, y equal x squared plus 9, and you write it a little bit differently. Alright, let's say we were working with two different equations, as a matter of fact, y equal x squared plus 9 and y equals 3x plus 5. And I've given you these two equations, one of them that I want you to graph, and one of them that I want you to, say, build an input-output table with. How do you know which one? Well, I could just rewrite it every single time, or I could give them names. And with function notation, that's what you do. You first of all give each equation a name. The names we will use will be single letters from the alphabet. The most commonly used name for a function is going to be f. So this first function I might call f of x. Now first understand that f of x and y are the same thing. F of x is just a better name for the y, the output, the range. So I would write f of x equal x squared plus 9. And since f is already used, you don't want to reuse the same name in the same question. You can reuse the name when you go to a new question or a new problem. But since f is already in use, I will name this one just the next letter in the alphabet, which is g. So this one would be called g of x if f of x wasn't free. So what I've done is I've named them. So if I tell you, go get function g and graph it, well, that's g right there. I could go to the calculator, get to y equal to, type in the 3x plus 5, look at the graph, and I would have done what you just told me to do. If I asked you to take f of x and plug in a 3, I can do that. And there's a way to tell people to do that. If I was to simply say f of 3, and notice this may look like f times x, but it is pronounced f of x, then f of 3 would be what you get when you go to function f, take out the variable, and put in the 3 exactly as you were instructed to do. So let's go back to our examples and use our function notation. Let me give you 2 or 3 functions to work with. Let's say we had an f of x equaling a 2x minus 1, a g of x equaling a 5x squared minus 3x, and an h of x being the absolute value of x minus 4. And let's say I was to ask you for g of 2. What would that be? Well, you go up, you get the function that I've named, you pull out the x, and pull it out wherever it was, and in its place you put a 2, and you start doing the arithmetic, and you've got it. What about an h of negative 8? What would that be? Well, you go up to function h, take out the x, put in the negative 8, and do the arithmetic. And you can actually get a little bit abstract. You could say, what is f of alpha? Alpha being a Greek letter. Well, you go up to the f, pull out the variable, put in the alpha. Since it's not a numerical value that you know, you're finished. So that's how the function notation works. You'll get the function you were told to get, and you put in exactly what you were told to put in, and you do the arithmetic.